All right, so let's put some things together here for testing a claim about a mean. Some important ideas. First, conditions that need to be checked. We've got our normal or our random condition like before, and our normal condition. We need to make sure one of these three things is in place to accomplish our goal. So 1, the population is normal. If that's the case, great. Then the sampling distribution of any sample size will be normal. If the sample size is at least 30, it doesn't matter if the population was normal or not. A sample of at least 30 will produce a sampling distribution that is approximately normal, so we're covered there. Or if the population isn't described as normal and our sample size is not at least 30, then we need to assess for normality by looking at the graph. Does the sample, when plotted in dot plot, histogram, box whisker, whatever, does it show any obvious skew or outliers? If the answer is no, then we can assume that the population from which it came from probably is normal and proceed from there. So this might take a little extra time on our end depending on what information we know. The next key difference here between this and testing a claim about a proportion is that our test stat is not a z-star value, it's a t-value. Values are the ones we use when dealing with sampling distributions for means, and the same one we use with confidence intervals for means. So our formula is pretty similar though. Your sample value, sample mean, minus the assumed null hypothesis mean, divide by the standard deviation of the sampling distribution, so standard deviation over square root n, for standard deviation of means. Now as for the p-value, I explained in words how to do this with the last example, so I'll explain in words again, but I will model it using the table this time so you can see this actually worked out. So first thing would be establish your degrees of freedom, n minus 1, and then you're going to go to that row. You'll find the two closest t-star values that would surround the one that we got from our calculation, and go to the top of the table to locate the tail probability at the top. The p-value would be in that range. Note, again, if we are dealing with a two-sided test, we will then have to double that range. Feel free to pause the video anytime to make sure you get all the notes that you need for this. I will make one more mention, and we'll see this as we go forward, not in our next example, but later video. We'll see that if your degrees of freedom don't fall directly on the table, you won't have every single possible value there. We always err on the side of caution and go to the next lowest one that is available. So we won't see that here, but we will see that in the next example on a future video. All right, so who needs an aspirin? After all these hypothesis tests, I might need one myself. Here's our example. The makers of Aspaway brand aspirin, that sounds phony to me, want to be sure that their tablets contain the right amount of active ingredient, which I'm not even going to begin to pronounce that. So they inspect a random sample of 30 tablets from a batch in production. When the production process is working properly, Aspaway tablets have an average of population mean equal to 320 milligrams of active ingredient. The amount of active ingredient in the 30 selected tablets has a mean of 319 milligrams and standard deviation of 3. We want to perform a test at the alpha equals 0.05 significance level of the following. So we're starting with the null hypothesis is the mean equals 320. We're concerned that maybe there's this different, so mean is not equal to 320. Note two-sided test here. Now, some questions might come up like, well, why wouldn't I just say the mean is less than 320 because my sample shows less than? Shouldn't I just pick that? Well, think about the issue that we're dealing with. If the production is not working properly, we would be concerned if the mean amount was less than. We would also be concerned if the mean amount was greater than 320. If it's different than 320, that's a problem. So that's why we want to test the two-sided test. The population mean, our parameter, is the mean amount of active ingredient in all Aspaway brand aspirin tablets. So let's first check that the conditions for performing the test are met. Our random condition, they said they inspected a random sample of 30. That's in the problem right there, so I just quoted that right out. Our normal condition, We just met that with our sample size. So I don't know if the population of tablets is normally distributed, the average amount of the amounts of the active ingredient, if it is actually normally distributed or not. But because my sample is at least 30, my sampling distribution of sample means will be normal. The central limit theorem is the one that applies for that. So this is a quick one to be able to meet those conditions. Calculating our test stat. So our T-star value, well, note, big mistake happens here. We need to make sure that we are using the sampling standard deviation, not the standard deviation that was stated above. That is the standard deviation of the 30 tablets. The sampling distribution of any amount of, like if we took sample after sample, 30 samples, found the average. 30 more pills, found the average. 30 more pills, found the average. And we repeated that. The standard deviation of the sampling distribution would be the standard deviation of our sample divided by the square root of the sample size. So this is the one we need to use here in our formula. Be really careful. Common mistake is to use the one that's given from the sample group, but the sampling distribution is what we wanted to work with there. Now that's going to yield a T-star value of negative 1.818. So now that I have that, I need to use the table to get the p-value. Okay, this is the time I wanted to show you how to do that. So degrees of freedom first. Since we have 30 values, we're going to be going to row 29 for our degrees of freedom, one less than our sample size. So here we are, and 29, right there it is. So my test stat, we said was negative 1.818. Well, we're not going to see anything negative. We'll just go to positive 1.818. So 1.818. Well, let's see here. There's 1.699. That's a little smaller than what I need. And 2.045, that is now over my test stat. So we know our test stat is falling in between these two values. So slide to the top of the table. There's the tail probability. So between 0.025 and 0.05 would be the area in the tail. Okay, now here's the deal. Remember how we said this is a two-sided test? We're going to have to double those values. So here I kind of summarize what I had noted there. Row 29, I was looking between those two values. The percent from the top was between these two values. But since it's a two-sided test, I have to double that range. So my p-value is somewhere between 5 and 10%. Okay. What does that mean? Well, we were testing at the 5% significance level, weren't we? So, since the p-value is between 0.05 and 0.10, which is greater than our significance level of 0.05, we fail to reject the null. We do not have convincing evidence that the amount of the active ingredient is different from 320 milligrams.